Thank you. Okay, so yeah, let's look at this boiling point elevation problem. We have a solution of sodium chloride, and we're just trying to figure out how that changes the boiling point of pure water. So in the exact problem, we have 5 grams of sodium chloride, and they're nice, and they even give you the water in 250 grams of water. And the question is, we also need to know, well, the question is, what is the boiling point elevation? So we know from studying colligative properties that if you take something, a non-volatile solute, and you dissolve it in water, you end up seeing the boiling point increase. And this is just a relationship, or there's just a quantitative relationship between those two things. We can use this simple equation to knock that out. So there's one of the semi-confusing thing about this is there's a lot of crossover in terms of the terms, in terms of the, what do I want to say, the variables that we use, like the, I can't think of the word, but we use, for example, like here we're using M. M indicates molality, in this case, convention, that's the word. The conventions for the different variables. M here indicates molality, right? But in like other equations, we use it as the mass. And as we'll see, Kb here is going to indicate this, like, I forget exactly what it's called, but it's this constant. It's a proportionality constant. So this proportionality constant for how the temperature changes depending on how much stuff you dissolve in it. When we go on to equilibria, you'll see we also use this capital K to mean equilibrium. And so it's just kind of an unfortunate overlap. I'm just going to call this proportionality constant. Boiling point change probably has some official name that's not that. And then I is just this Van Hoff factor. So Kb is something that we usually give you, and indeed in this problem we did give it to you. And so Kb is given by 0.512 degrees Celsius per m, which we'll assume here is per molal. Yeah, and then it's just a matter of kind of making sure that you calculate everything correctly. So probably the most confusing part of this is just what does I equal. And so for ionic compounds, we generally have to worry about I being equal to something that's not just one. For compounds that are not ionic, so things like sugars or, I don't know, there's, most compounds, honestly, I is just going to be equal to 1. But if what you're putting in a solution will dissociate, then we have to worry about what I is equal to. And so we have 1 mole of sodium chloride that we're dissolving, but practically speaking, we end up with 1 mole of sodium and 1 mole of chloride in the solution. And so we have 2 molar overall. And so for here, this, I is going to be equal to 2. So I is essentially just like the sum of the coefficients of whatever the net, not just the net, but whatever the ionic reaction is. And so that's what we're going to plug in for this value here. Kb is something we're given, and then molality is kind of weird. So molality, be sure to differentiate between molality and molarity. Molality is given in moles of solute per kilogram of solvent. So here we're given whoever wrote this problem, the units are a little bit confusing. Grams per mole. It's at 0.512 degrees Celsius per mole. Maybe it's just per mole. So yeah, so even more unfortunate with the units in this one. So we give you the molecular mass of sodium chloride. It's 58.44 grams per mole. And so to calculate the molality, you just want to convert the 5 grams into moles. So let's go ahead and do that. So to do that, hopefully that's not super challenging for you. We're just going to divide it by the molecular mass. And we come out with 0.086 moles. And so the molality is going to be equal to 0.086 moles divided by the kilograms of solvent. So remember, we have 250 grams of water. So you just want to make sure you convert that to kilograms. So we're just going to divide that by 1,000 grams. If I can punch this into my calculator correctly, it's 0.25. I get 0.344. All right, M, where M here stands for molal. So question about the formula sheets or conversions, et cetera, for the test. These tests are open, notebook. The only thing you're not allowed to do on the exams is to talk with your peers. So, you'll have whatever formulas and conversions you need and access to Google and stuff. So you can use those resources. So, no, I guess the answer is no, you don't need to memorize the formulas. I'll let you know if a formula I think is worth memorizing. But obviously I have no way to test you on that. All right, so we've got the molality, and we've got Kb, and we have I, so we can calculate what delta T will be now. So delta T is going to be equal to, I'll rewrite the equation just so we can see it, to this, which is equal to 2. So I is just a dimensionless quantity. And then Kb, which we're given in the problem as 0.512 degrees Celsius. Per molal. Yeah, and then we want to multiply this times the actual molality. And so you see these units cancel out. And we come out with the temperature change. Assuming I did my calculation right, it's just 0.352 degrees Celsius. And so this is pretty normal for these changes in boiling points. It takes a lot to nudge the boiling point up. So you should generally see small temperature changes. So dissolving 5 grams of sodium chloride in a water only changes the temperature of the boiling point by a fraction of a degree, at least Celsius. And this is kind of our experience, right? If you salt water before you boil pasta or ramen or whatever you're making, it's not like it takes like gratuitously more heat uh, to bring that to a boil, or the water that if you that boils off, it's not like super scalding or something compared to normal boiling water. Um, and so that's how you run through these calculations. So the things to be careful of here, though, are that we're working in molality and not molarity, and those are two different things. Molality is moles of solute per kilogram of solvent. This is a little bit weirder than what we usually use, or it's weird compared to what we usually use, which is moles of whatever per liter. And then the other thing that you have to worry about is the Van Hoff factor, which is dependent on more or less just whether or not you have an ionic compound there. So, just whatever some of the coefficients are, the products, if you write out how that ionic compound associates. Otherwise, just keep track of your units, and these problems end up being reasonably, as reasonably straightforward as problems can be. If you look into a textbook, I don't know what it says on the GChem website, but if you look into a textbook, the problems can get a little bit more complicated than this. They can ask for, I don't know, how to calculate like molecular masses and stuff based on changes in temperature. I don't know. I wouldn't put a lot of time into that. I doubt we'll ask you a question like that on the test. The main thing is just to have some idea that, like the global thing is that temperature changes if you dissolve stuff into a pure solvent, and then that is, a linear relationship, and you can describe it with these simple equations. That's kind of the general takeaway. Okay, so that's colligative properties. There's a lot to unpack with colligative properties in terms of free energies and all this other enthalpy and entropy stuff. But in terms of just kind of calculating stuff out and kind of getting the global ideas behind it, how things change, it's reasonably straightforward. Boiling points go up, freezing points go down. And then we have these simple linear relationships that we can use to describe them. Okay. Yeah, so the next topic that we get into is equilibrium. And so I think we have some problems up for that. I think it says Rice tables. So there's two parts to the equilibrium thing. I mean, there's two parts generally to everything where, you're looking at things conceptually, and then you're also looking at how to do things quantitatively. Equilibrium is something that is not, I mean, there is a conceptual part to it, but it's the students struggle a lot with the quantitative aspects of this. So unlike, this colligative property thing where we just worked out, where it's just like, okay, I plug in some numbers and it spits out a new number, and, I have pretty good amount of confidence that that's correct. In chemical equilibrium, there's like a little bit more subtlety, I think, in terms of how you develop your quantitative process, and it can get confusing. So be prepared to spend a little bit of time on this and to, I don't know, be a little bit confused, I think, when you're working at problems. I wouldn't save this, I guess I'd say, for, the night before the exam or something. This is something you want to put more practice into. So if you're kind of behind, I guess, in the material, which, it happens, I would go back or like be more, I would consider kind of skipping ahead, just starting in chemical equilibria, and then going back and looking at the phase diagram stuff and the colligative properties later. Because if you have to cram something, that stuff is better to cram than the chemical equilibria. This stuff is kind of harder to get. Okay, so if you've watched the lecture for that, the main thing that we deal with for equilibria is I mean, there's a lot of stuff there, but the main thing we'll be dealing with is just the equilibrium constant. So very famous, let's see, very famous reaction. So how am I doing on time? Good, we're good, a good amount of time. So equilibrium, like just globally speaking, before we kind of get into what I stepped away. What did he say to cram? I said, I didn't say cram anything. I said, just don't cram equilibria. That's not a good idea to cram. If you have to cram something, cram the other stuff. Yeah, equilibria has a lot of applications in a whole bunch of different fields. The equilibrium constant specifically. The one that comes to mind that's most relevant is for drugs. When you're dealing with drugs, equilibrium constants come into play because you need very strong, inside of your body, there's these, the targets that you're trying to treat, these big proteins and biomolecules, where drugs will go in and bind to them through these non-covalent interactions like we've talked about. The equilibrium constant for that binding event has to be extremely high in order to get some sort of drug activity. So people who deal in biochemistry in general are worried about equilibrium constants, and people who develop drugs are also very concerned with equilibrium. And so that's sort of the bigger application. The more obvious application that's a little bit less complicated as a beginner topic is in just looking at things like chemical engineering, where you're trying to optimize a process to get the maximum amount of product out of it. And so that's what we're going to kind of start out here. And those are going to be the general problems we work on. Eventually, we'll get into acid-base equilibria, which just kind of builds on this. But if you go on to take more advanced courses, you'll see these things kind of pop up again and again. So this reaction is super important. You don't have to memorize this reaction. It's super important to us as a society, though, because this is how we get fertilizer, which is, everything, I think, in terms of just like agriculture. So the process is called the Haber process. It was developed by this this guy named Fritz Haber, who's famous for this process, which he got a Nobel Prize for, and also famous because during World War I, he developed chemical weapons for the Germans, and released chlorine gas on these French armies. So he's also kind of the father of chemical warfare, which was eventually what after World War I was banned in military conflicts because it's pretty gruesome. So anyway, it's kind of an interesting reaction in general, but this was developed kind of in the early 1900s, and it's still the way that we make fertilizers. So ammonium nitrates and these types of things are made with the reaction. Anyway, just a little bit of history. In terms of figuring out what's going on here, so the equilibrium arrows are telling us that at the end of this reaction, so you start the reaction, let's say with some amount of, let me see how I want to present this. Let's actually, let me write it the other way, which makes way more sense. Yeah, okay. So because equilibrium, not the lesson I wanted to teach, but because equilibrium reactions go in both forward and backwards directions, you can write them either way. But this is the more familiar way to write it. So usually what you're doing is you're taking hydrogen gas and then nitrogen gas, which is, we have plenty of that in the atmosphere, and you're trying to get that to convert over to ammonia. And traditionally, when we're kind of first starting out learning chemistry, we just have an arrow that goes in one direction, which would indicate that, I take this and I mix it with this, and I'm concerned with how much of that we end up getting. And some reactions do more or less go almost all the way to completion. But most reactions, or many reactions, will actually have this equilibrium. So at the end of this reaction, so I start out with some amount of this and some amount of this. At the end of the reaction, I'm going to expect to have formed some of this, but I'm expecting to still have some of the reactants, the nitrogen, the hydrogen there. That's basically what the equilibrium is telling me. And so how much is going to be there, or what the exact proportions of these things are going to be, is going to be determined by a value called K. So for this reaction, K is equal to 6 times 10 to the minus second. The units on these get kind of weird. Liter squared per mole square. And this is true only at constant temperature. But so at 500 degrees Celsius, we know that K is always equal to this value. Usually we're at constant temperature, so that's not something you typically have to worry about. But it is important to know that it's only true at constant temperature. But this is important. So this K value is important because it has this relationship with the products and the reactants. Which is that you can take the products and divide them by the reactants. And we raise them to the power. This will be a source of confusion at some point or another. We raise them to these powers that are out front, the coefficients. So, you know, we have a 1 here that we're not drawing, just like we don't have to necessarily draw the 1 there, but I'll put it in just to be explicit. But so this relationship allows me to calculate what the final concentrations are going to be of ammonia, hydrogen gas, and nitrogen if I know the initial concentrations. So remember when we start out doing reactions, you know, we'll give you something like, it might be like, oh, if I have like A plus B goes to C, we would say, you know, we've got 1 mole of this and 3 moles of this. How much of this do we form? And you might go through limiting reagents and all this kind of traditional stuff to figure out how much C we're going to form. Now we're saying, well, for equilibrium reactions, you can't do that anymore. So you can't just take the number of moles that you start with and assume that the molar ratio is going to hold for the amount of products you form. We have to take into account the fact that the reaction doesn't go 100% to completion. This is a more complicated calculation to deal with. And so let's take a look at what these problems are set up with. So something that might be like, we could say like, the initial concentrations of hydrogen and nitrogen are both 1 molar. What are the concentrations hydrogen, nitrogen, and ammonia at equilibrium? Standard problem. So we're given some initial concentrations here. That's an important thing to recognize. We're saying we have these initial concentrations, and they're both the same in this case. They don't always have to be. But we're given initial concentrations of 2 of the reactants, and then we're asked, what we're trying to figure out is, you know, what are the concentrations at equilibrium? So now we're saying, okay, what do the concentrations end up being? So all we're doing is the same thing you've always done in chemistry, or like in the beginning of chemistry, which is I have a certain amount of reactants. How much products am I forming? Now things are just more complicated because the reaction doesn't go to completion. So traditionally, we would just say, okay, I've got 1 mole of hydrogen, and I can come back up and look at this reaction and say, okay, the stoichiometry is 3 to 2, and use that to end up just calculating what the final concentration would be. But that assumes that the reaction goes 100%. And we're saying, no, that's not true. And in fact, it doesn't go, looking at the K value, it doesn't go anywhere near 100%. It goes to a much smaller amount. So the bookkeeping method that we typically use for this is to use something called a Rice table. Let me let's rewrite this equation again. Yeah, so what the way we go about solving these problems, we use something called a Rice table. So Rice stands for, I forget, it's like Rice. So this would be the reaction. This would be initial. This probably stands for change. And this is at equilibrium. And so this is just a way to keep this thing organized as we go through the calculation. Let's see. So what are our initial concentrations? That's what we're plugging in here. So you can kind of think about it like I'm taking hydrogen and nitrogen and I'm putting it into a reaction. I'm putting them into a reaction vessel, and then I'm waiting to see what happens. So when I first put them in, I expect their concentrations to be exactly, I'm going to leave their units off, but I'm expecting their concentrations to be exactly 1 molar for both hydrogen and nitrogen. How much ammonia do I have there initially? Just 0 molar. The changes, we don't know. That's what we're trying to figure out. But we do know that they're going to have a very specific relationship. We do know that they're going to have a very specific relationship. And that is that for every amount of nitrogen, so if I have 1 mole of nitrogen, I'll come back and explain this in a second. So for nitrogen, it's going to be minus X. But for every, let's say, mole of nitrogen, that's a good way to explain it. For every mole of nitrogen that gets converted, I'm going to convert 3 moles of hydrogen. And then for every mole of nitrogen that I convert over, I'm going to gain 2 moles of ammonia. So this piece here, the change, tends to just be very confusing. Where do those coefficients come from, et cetera? So you got to spend some time on that. But really all you're saying is you're doing the same thing that if you understood what you previously done to calculate yields and things of that nature, we're just saying the same thing here. We're saying that these coefficients tell us the ratio, or tell us how these things change together, right? This says that for every 1 mole of nitrogen I have, I'm going to form 2 moles of ammonia. So I don't know how much nitrogen is going to get converted. That's what I'm calling X. But I know that however much gets converted is going to result in 2 times as much ammonia. That's where these coefficients that are out front are coming from. And then I just want to write out the equilibrium condition, or my equilibrium expression, in terms of this variable X. And so I just combine these terms. So I'm saying that I start out with 1 molar hydrogen. I'm going to lose, let's just call it moles. I start out with 1 mole of hydrogen gas. I'm going to lose 3x from that. I don't know what x is. That's what I'm trying to figure out. And so I can write that expression out. At equilibrium, I'm going to have 1 mole per liter or whatever, 1 mole minus some amount, 3x. And the same is true of nitrogen. I'm going to start out with 1, but then when I come to equilibrium, it's going to lose some amount, and that amount we're going to call minus x. And then finally, here for ammonia, we didn't start out with any. And we know that we're just going to gain 2x of that. So we start out with none, and we're going to actually pick up some ammonia at equilibrium. And so the value of this method is it gives you this really nice algebraic form for everything, and we can take that and combine it with k to solve the problem. So we know that k is equal to this number. And this number is constant. This is not going to change. So you can imagine that there's a lot of different values that we can plug in for hydrogen, nitrogen, and ammonia that will satisfy this equation. You know, I could have this equal to 1, and this equal to 1, and this equal to the square root of 6.02 times 10 to the minus 2, and that will give me that number. So there's a lot of different concentrations of ammonia and hydrogen and nitrogen that will satisfy this. The only way to really know with your final concentrations, you have to be given some initial concentrations to start with. What am I trying to say here? I'm saying that the values of hydrogen, the values of the concentration of hydrogen, nitrogen, and ammonia can be a whole bunch of different things. The only thing that holds true is that this number does not change, at least at 500 degrees Celsius. That number will always be the same. And so now I can go ahead and plug in some numbers here. I can say, okay, I've got 2x over 1 minus 3x times 1 minus x equals 6.02 times 10 to the minus 2 liters squared per mole squared. Ugh, God, I hate solving these things. Okay. From here, we just have to solve this. So there's two different ways that this can sort out. One is, see how my algebra skills are not great anymore. Let's see, we've got 1.
Forgot the square on 2.
Oh yeah, thank you.
And the cube
I
on
need
one.
those. If that makes it even more of a messy. Hold on. So that's squared. Yeah, I think we're good. And so then that is equal to 6.02 times 10 to the minus 2 liters squared per mole squared. At this point, it just becomes an algebra problem. I'm trying to think if there's some shortcut or something here. So I'm going to solve this using algebra. At that point, it's just a math problem now. Let's see. I'm trying to think if we could just make some assumptions here to make our lives a lot easier. So usually one way to think about this, or one thing to consider, is that for values of k, so when we're looking at, I'm not sure if this will hold here, but I want to do it because I don't want to have to deal with that cube. So this is, you can see already how these things start to get pretty messy. Okay, so if we're looking at this reaction, and we're considering K, for large values of K, so when K is very large, so like let's say K is much greater than 1, reactions are product favored. So, if K is equal to 1 million or something, then I know that I'm going to form a ton of ammonia. But if it's the opposite direction, let's say K much less than 1, reactions are reactant favored. And this falls out if you come back and if you look and analyze this equation, you can see that the products are in the numerator up here. So naturally large values of K are going to favor large numbers in the numerator. That's where this piece down here is coming from. But here we see that K is not very large, right? K is much less than 1. It's 6.02 times 10 to the minus 2. And so sometimes what you can get away with doing is saying, well, I don't know exactly what X is going to be, but I know X is going to be small because I'm not going to form much ammonia, meaning that I'm not going to lose much. If the reaction is favored to this side, that means that the concentrations of hydrogen and nitrogen aren't going to change very much. And so we can guess, or we can make the estimate and say, well, whatever it loses, let's just say that it's probably not super significant, and we can simplify things in this bottom part of the equation and just get rid of the x's altogether. And then the equation becomes much simpler to solve. So we're not trying to go on a math voyage here. I hope this works because I don't know how to solve that cube if not. Or at least I don't want to. So I'm going to punch this in my calculator. God damn it. Yeah, I picked a bad starting point for a problem. So yeah, so in this case, we see that the x actually is significant. So generally, as a rule of thumb, if x, let's see, if x is greater than, I don't know, like 10%.
I think you forgot to divide by 4.
What's that?
Yeah, you
Oh,
forgot to divide by 4.
Oh yeah, okay, maybe that'll help me out. Gets us closer. Okay. So yeah, so with the dividing by 4, it kind of gets us close enough that we can do this approximation. Not feel super bad about it. I don't know. It's not great. But yeah, so we come out with x is equal to 0.12. But generally, you want x to be less than 10% of whatever concentration you're starting with. So yeah, so here it's 0.12. It's a little bit bigger than we want it to be. So our whatever our approximation isn't perfect. But we can take this value and we can plug it back in and say, and figure out what our final concentrations are. So yeah, so generally speaking, we try to give you things that are pretty solvable, so not things that involve cubes in them or that require, I mean, the most complicated it ever gets is you having to use the, either use an approximation or use the quadratic formula to solve things. It misses the point to get kind of bogged down in the algebra here. Ultimately, what we want to do is we want to figure out what the equilibrium concentrations are. And so we can come back up and take this Rice table. I'm going to cut it. Try not to get overly concerned, I think, at this point with like when to do approximations for how to solve the algebra. Just assume that we've solved it properly. And focus more on like this chemistry component that can be a little bit confusing. So then what does this tell us? What is x at this point? X is the change. So we come back and we say, oh, okay, right. I remember now. After punching through all this algebra, which is a pain in the ass, I remember what x was we're originally calculating. It's just the change in the values of the original concentrations. And so I can come back and figure out what H2 is equal to. H2 is equal to 1 minus 3x. So it's equal to 1 minus 3 times 0.12. Yeah, not too bad. This is a little bit off from the actual equilibrium values, but we're gonna roll with it. So it's equal to 0.64 molar. What's our nitrogen concentration going to be? It's going to be equal to 1 minus x. Right, so we're defining our equilibrium values as these expressions. And so it's just going to be equal to 1 minus 0.12. Which is 0.88 molar. And then finally, what's our ammonia concentration? That's just going to be equal to 2 times x, so 2 times 0.12. So 0.24 molar. Yeah, the actual equilibrium concentrations, if we go through and work through the math, because I have the answer in front of me, are not exactly this. Don't worry about that for now. But so the main thing to come across here is this workflow for the problem. So you write out your Rice table, and we'll talk more about this on, let's say Friday, on Monday. You write out your Rice table, and then you write out your equilibrium constant expression. And then you use these expressions you come up with for the equilibrium from your Rice table in combination with what the equilibrium constant is, and that gives you this constraint on the variable, which usually, in this case, is a little bit more painful than it should have been, but usually allows you to solve for x. And that's what we're trying to do here, right? So just some math. There's some approximations we can make. So usually we can just say, screw it. We're going to say that x is equal to x, or whatever the initial concentrations are, approximately equal to what they're going to be at equilibrium. This turned out not to be a great approximation here, but it's fine. But anyway, after you solve for x, we come back and we plug that back into the equilibrium expressions that we came up with, these little algebraic expressions, and that allows us to calculate our concentrations at equilibrium, right? So it's not a super straightforward problem solving thing. So I think the reason this gives students problem is because we get so used to doing things like we did with the colligative properties, where it's like, oh, okay, I have this equation, delta E T equals I times KB times molality, and I just plug in these numbers and I get out, it spits out this nice, it spits out whatever I'm looking for. Here, there's like, a lot of different steps. It's not just plug in some values here. It's before I plug in these values, I have to derive some nice algebraic relationships from the chemical equation. And this becomes really problematic for students. So it takes some time to sit with. Question in the chat is, if K equals 1, this has become like non-equilibrium equations. So at 1, you have about 50%. Those are good things to think about. But at 1, you have 50% products and reactants. It's really at like K equals 1 million that it becomes like a non-equilibrium equation. So extremely large values of K, you can start to treat this like a non-equilibrium situation where you just assume that you form 100% products. As you approach 1, you're about 50-50. And then as you go below 1, you're starting to be more reactant heavy. Units for the ending values would be molar. Yeah, so on an exam, we wouldn't give you one that was required this much kind of aggravation. For me, generally I try to give you problems that are not algebraically miserable, because I don't, the quadratic equation, even when I work it out, it's like really easy to forget a sign. This one is, I don't even know I have to think about this and carefully. This one, I'm not sure exactly how you'd solve by brute force. But yeah, I guess on an exam, because this one failed the 10%, you would go back and plug it in. And the actual equilibrium concentration here are a little bit different than the ones that I calculated. But you've got access to Google. Conceivably, you could do it, but that's not really, I think my goal as an instructor, to make sure you can solve equations or solve complicated algebraic equations. Just getting the workflow for the problem and kind of understanding what you're doing is more important. So I just picked a bad set of starting conditions, I think. Yeah. So anyway, so on Monday, we'll work through some other problems, more rice tables to try and get used to this, but try and spend some time like practicing and maybe watch the lecture videos or look up some other videos on YouTube. The GChem worksheet's harder than we'll do in class. I don't know what's in the GChem worksheet, so I can't say. Like the phase transition worksheets, the chemical equilibrium worksheets. What are the X's for I? Oh, for colligative properties. I can't remember what's on those. Probably for colligative properties, or maybe for colligative properties they are. For equilibrium, they're probably on par with what you'll see in the exam. I tend to hit colligative properties a little less hard than other people. I don't know. They seem less chemistry oriented to me. But yeah, look at the GChem website. Worksheets and stuff are really good places to go for equilibrium problems. So go and mess around with those. And otherwise, well, don't have too nice of a weekend. Have a pretty good weekend. Find some time to relax, but make sure that you work on this equilibrium stuff a little bit, because it moves pretty fast. And we have next week, and then we have an exam the week afterwards. So it's not like there's a crazy amount of time to get this, and it's not super fun. I don't know how to say you're not going to be able to, but you're not going to be able to like internalize it in a really good way just in a weekend. Try not to cram this and go back to that. Try to spend some time on this week. And try to just take your time and work with the problems. This is not something that really lends itself to just kind of brute force plugging in numbers and moving forward. You kind of have to step back and think about what you're doing in a little bit more careful way, which is harder to do. So, all right. Again, why my iPad is telling me a different time than my computer. It is 9:54, right?
Yeah.
Yeah. Okay. I don't know what's wrong with my iPad. Maybe it froze up. All right. Anyway, so I will see you guys on Monday. Spend some time on equilibria. And yeah,
All
that's,
right.
that's
Thank
pretty
you.
much it.
Thank you.
This will be the last thing that we go over before the exam. Yeah, I don't know what's going on. My iPad's in a different world. Bye, you guys.
Thank you.
Yeah, you're welcome.